Hello and welcome, everyone. Thanks for joining us for this O'Reilly Media Live course. I'm Brittany Brady, and I will be your facilitator for the course. We're excited to have you here. We'll be kicking things off shortly, but before we dive into the content, I'd like to go over a few quick housekeeping notes to help you get the most out of today's session. At the top right corner of your screen, you'll see a set of widgets. The two we'll be using the most today are the Q&A and attendee chat. Feel free to open those up now if they did not open automatically when you joined. We encourage you to jump into the chat and be part of the conversation. This session is being recorded, including any participation from attendees. So if you take part in the chat or Q&A, please do not post any personal information like your email address because it will be included in the recording. You'll receive an email within the next 24 to 48 hours with a link to the session recording so you can review or catch up on anything you missed. Please note that the chat feature should not be used if you're subject to regulated communication restrictions. Also, keep in mind that others in the audience today may include fellow professionals, vendors, or even competitors. We hope you'll take advantage of the interactive tools, but please be cautious about what you choose to share. You can complete the feedback survey anytime by clicking More at the top right corner. It will also open automatically at the end of today's session. We'd love to hear your thoughts, and thanks for sharing your feedback. I'm going to hand things over to your instructor now to kick off today's course. And with that, let's get started.
All right, awesome. Thanks, Brittany. So welcome to this crash course on the GCP Professional Machine Learning Engineer exam. I'm Richard Bryant, and I'm going to be your instructor here. And I appreciate you all coming and hanging out with me for 4 hours here. I know for many of you joining, it's probably very early in the morning. So especially if you're over on the West Coast, it's 5 in the morning over there. So thank you all for being here, and I hope to make this as engaging and as useful a use of your 4 hours as I possibly can. So just very briefly going over what we're going to be doing here. So obviously the GCP Professional Machine Learning Engineer exam, it's a big exam. There's a lot of content that's covered. I cannot possibly do a deep dive on every single topic because we're only here for 4 hours. If we were doing that, we'd be here for 4 days, right? Obviously, we're going to cover some of these hot topics like data processing and machine learning in GCP using the right tool, feature engineering and feature crosses, some of these more fundamental machine learning concepts that the exam tests on, like the bias variance trade-off, data leakage, while training and serving, so on and so forth. Orchestration frameworks is going to be a big piece of the final hour that we have here together. A few things. If you have not been reviewing it yet, I don't know when y'all joining here plan to take the exam. I'm sure for some of you, it might be in a couple weeks. For some of you, maybe a couple months. For some of you, could be next year. Who knows? The very first thing I would do is review the exam guide and go through all the sub-bullets. What I will say with the sections is it is not always obvious. Let's say you're looking at an exam question. I can almost guarantee you're not going to go look at that exam question and then you're going to think, aha, that's section 3 on scaling prototypes into machine learning models. You're just probably not going to be thinking about that. Maybe the one exception I can think of is like section 5 on automating and orchestrating machine learning pipelines. Just because that whole concept around orchestration frameworks is such a critical piece of the exam, and it's actually the component that carries the most weight. So I wouldn't get too hung up necessarily on the differences between the various sections here. And it's actually not the way that I've structured this course myself, because it's just not the way that I think about it. The way that we're going to do it in this course is we're going to be going through some fundamental like machine learning metrics first. I'm going to walk you and just hit you with a whole bunch of different GCP tools so that you can just know the difference between the tools, the different use cases for all of them, so on and so forth. We're going to go through feature engineering, some of the high-level modeling stuff. We'll go through hardware, monitoring, and then our last section here, what like the last hour of this course, we're really going to hit security and pipelines. And the other thing we're going to do here is right here in this course, we're going to go through 30 exam questions. That's going to be the goal here. It's ambitious, but we'll get through it. Now, what I'll say with questions on the exam, there is definitely a spectrum out there with how difficult these questions are. Literally, you'll be going through the exam, and some of them you'll think, oh, this is really easy. And some of them, it's like, this is a really hard question, and they're going to scare you. There's definitely a spectrum, and I've tried to represent the spectrum of difficulty of the questions as much as I possibly can in this course. So as far as where I've sourced the questions, there's the official Google Cloud Professional Machine Learning Engineer Study Guide. This book is pretty good. It might be a little out of date now because the exam has updated a little bit, but the content on there is still generally quite good. Journey to Become a Google Cloud Machine Learning Engineer by Logan Song is another good one. Google Cloud's official sample questions and documentation. Whenever you can use that as a reference, you should. What I will say up front is Google Cloud has their own official sample exam, and that is definitely the most challenging resource out there for exam questions. I remember the first time I took it, I went through that, did not score extremely well, and was a little bit demoralized. But, you know, they provide good explanations. You learn from those questions. And, you know, if you're scoring at like 50% on those questions, I can virtually guarantee that you're going to be in good shape on the actual exam, because those questions are much harder on average than the questions on the actual exam. So, and I've used that as a resource for creating some of the questions for this course. So, without any further ado, I'm going to move into our content here, just starting with some just high-level fundamentals. We're going to go through that, go through some sample exam questions, and then we're going to move into some of the GCP tooling. But one of the most fundamental things that we kind of have to think about with really any type of machine learning problem in general is, when should you be using machine learning in the first place? Sometimes you'll see questions on the exam where it's like, what's the appropriate use case for this? And the answer might be, it has nothing to do with machine learning in general, because, you know, the classic example of that is like weather models. For instance, like you have pre-established weather like forecasting models, which aren't necessarily using new machine learning techniques. So you need to understand if there are existing tools that are better than machine learning. As you set up and frame a machine learning problem, you have to ask various questions like, what's the intended impact? What does success look like on the problem? What's the budget and time frame? Is the problem even solvable using machine learning? These are sort of the questions you have to ask. And then as far as the different approaches for machine learning are concerned, it's critical to know the difference between supervised learning and unsupervised learning. Sort of what's the difference between those, and then just unpacking that a little bit more within, right? So for supervised learning, that's the case when we have a labeled data set that we can use to train a model. So then you've got, well, what kind of label are you looking at, right? So for classification, your label is a category. You could have multiple categories. In many cases, it's binary, like a 0-1 sort of thing. Or it could be a regression problem where you have a continuous response to predict. Similarly, with a forecasting type of problem, you have time series data and want to predict the future given rows and observations that you have from the past. This is all in contrast with unsupervised learning problems, where we have no labels and we group them ourselves. So there are different types of unsupervised learning problems. Clustering is an example where we create groups based on similarity within and difference between. And there's a specific kind of interesting use case around that, around topic modeling, when we take documents and classify based on commonality of words and or sentences. One of the topics which gets I virtually guarantee that you're going to see a few questions on the exam come up about this, is around classification metrics, specifically in the case of binary classification problems. You've got all these different metrics out there, like recall, precision, you've got the F1 score, you've got the areas under various curves. I virtually guarantee you're going to see questions about those metrics, what's appropriate. Maybe it lays out, here's this thing that was calculated based on this confusion matrix or something like that. You're going to see questions like that, and in an ideal world, those should be some of the gimmies that you want to make sure you get those right. So you want to know the definitions of these. Recall will be equal to true positive divided by true positives plus false negatives. And precision is true positives divided by true positives plus false positives. I have always found it easiest to remember the difference between these metrics in the case of a problem. So, for example, when I was a younger newbie data scientist, like 7, 8, 9 years ago, I remember working on a sepsis prediction model, and it was really easy to think about this in terms of predicting sepsis, because recall would be the percentage of the cases with sepsis that we were correctly able to predict. Precision would be the percentage of the time when the model was predicting that individual to have sepsis, what percentage of the time did they actually have sepsis? Okay, so thinking about this again in terms of some kind of problem, whether it's sepsis prediction or it's maybe something else that you're used to, that is probably for most people going to be a lot easier than just remembering what this confusion matrix looks like in your head, or just remembering in terms of true positives, true false negatives. Like, all that stuff can be a little bit more abstract, or at least it is to me. There's also the areas under various curves. So the area under the precision recall curve, as well as the receiver operating characteristic curve. So AUCPR, AUPRC, whatever, I've seen different acronyms for that before, shows us the relationship between precision and recall for different classification thresholds. The specific use case for that is that it's very useful for highly imbalanced data sets. That is, if your data set has a lot more of the positive class compared to the negative class, or other way around. AUC-ROC, area under the receiver operating characteristic curve, is still very generally useful and shows us the relationship between the false positive and the true positive rate. These things are scale invariant and threshold invariant, which makes them very useful metrics. So it's just useful to have the visualization of these curves in the back of your mind. So for instance, with the ROC curve, a perfectly random classifier would have an area under it of 0.5. It would literally be like a straight line that runs just like y equals x, and the area under it would be 50%. A perfect classifier would run literally straight up, they get to the top, and then run to the right. The area under that would be 1. There's not a hard and fast rule for an ROC curve about what's a good classifier, because it just depends on the individual problem that you're working on. But generally, I mean, a lot of us get pretty excited when we see an AU ROC of like 0.7, 0.75, somewhere in there. 0.8, you're doing really well. 0.9, I start worrying about data leakage and that I did something wrong, but that's me. I talked about imbalanced data a little bit. This is another thing that the exam does like to ask you some questions on. But again, in imbalanced data, we have vastly unequal samples of the different classes. This is, in fact, how a lot of real-world machine learning classification problems work. But for instance, a spam email filter where out of all emails, 1,000 are not spam, but only 10 are spam. So about 1% fall into that positive class. That's, again, very common, and you have to know how to deal with things like that. So there are different ways that you could deal with this in a random sampling. You could oversample by duplicating cases from the minority class. There's also SMOTE, which is a specific use case of that, where you're creating essentially synthetic data with the goal of oversampling. But then there's undersampling, where we're removing cases from the majority class, with, again, the goal being to get a more equal distribution between the two classes. I threw this in here because you might see a question or two on the exam about this overall responsible AI framework. I would encourage you just to read Google's documentation about that. A lot of these are fairly straightforward: being socially beneficial, not enforcing unfair biases, be built and tested for safety, we're building things for humans, incorporate privacy principles. We'll have a whole section about that later in this course. Upholding high standards of scientific excellence and being made available for uses that accord with those principles. And just review this before you go take the exam. It's one of those things where you do that, you should be in good shape. All right, let's go ahead and try some exam questions. This will be our first little section here where we'll see if y'all are awake and we're paying attention, and how ready we all are to handle these problems. So let's move on here. So you work for a car manufacturer and are asked to detect hidden cracks in engines using X-ray images. Missing a crack could mean the engine could fail at some random time while someone is driving the car. Cracks are relatively rare and happen in about 1 in 100 engines. You are going to build a machine learning model to classify if an engine has a crack or not. If a crack is detected, the engine would go through further testing to verify. What metric would you choose for your classification model? Let's use the interface here to submit your answer. I haven't seen any responses come in, but go ahead and do that if you can. And let's go over the answer in think about this for about a minute, and then we'll go over it. I see the submissions coming in. Awesome. There's a little bit of a lag on my end. Keep going, keep submitting your answers. We're going to close this one in about 20 or 30 seconds. All right, gonna close this one in 5, 4, 3, 2, 1. All right. Okay. So more people chose precision. So the answer here is actually recall. So we want to be detecting as many of these cracks in the engines as possible. So just a couple of these that we can rule out right off the bat. Nobody selected root mean square error. That's good. Root mean square error is a regression metric, not a classification metric. Similarly with accuracy, that's almost never what you want to optimize for. Models will, sometimes you can pick between different models with accuracy, but that's not an important metric from the user's standpoint. Especially with imbalanced data, because you can literally say nothing has a crack and then you're going to be 99% accurate. So again, accuracy is not really useful here. In this case here, if there's a crack, that's a pretty devastating type of situation. We want to detect as many of those as we possibly can, just because the cost of having a crack and it slips under the crack, and pun not intended there, the cost of a crack is really devastating. The question told us here that if there is a crack, it goes through further testing to verify. So it's maybe not as important that the model is necessarily all that precise. But again, like the key concept here is if there's a crack, that's a really bad situation. So we just want to make sure we collect all them as much as we possibly can, because the engine could fail. Nobody wants a failing engine. Let's move on to the next question here, which is the data science team has built a deep neural network to monitor and detect defective products using the images from the assembly line of an automobile manufacturing company. As a Google machine learning engineer, you need to measure the performance of the machine learning model for the test data set and images. Which of the following would you use? AUC, precision, recall, or true positive rate? Let's take a minute or so on this one. I saw a question in the chat about similar to cancer problem, right? Yeah, like this is one of those things you sometimes have to think about with these questions about like, what's the cost? Like, what's the true human cost of us missing something? And, you know, again, you have to read a little bit more into it in terms of how the question's designed, but typically missing cancer is a bad thing. missing a crack in an engine is a bad thing too. Let's think about this for another 30 seconds. All right, let's take another 5-ish seconds. Trying to get the participation rate here up on the questions. Make sure you get an answer in, even if it's your just going on instinct. Well, 5, 4, 3, 2, 1, and the answer is AUC. So when you see this as an option, I am not gonna tell you make a hard, fast rule and always pick something like that. I'm just not gonna tell you something like that, because I can't imagine all the different possible permutations of questions that Google can ask here. But generally, the thing with any kind of area under a curve is it's kind of balancing for different metrics, right? Like AUPRC is going to give you some kind of, it's almost like a weighted average between precision and recall. Similarly, like an area under a receiver operating characteristic curve is going to balance between recall and specificity. So you want to go with AUC here because it is classification threshold invariant, and it is the best way here to measure the model's overall performance. Again, that's going to be better than precision or recall by themselves. And I'm not really sure here what your true positive rate is going to give you. Again, your AUC here is going to be your go-to. AUC question in the chat about what is AUC. AUC, broadly speaking, is area under the curve. Now, that could mean area under the receiver operating characteristic curve or a precision recall curve. This question didn't actually specify, which, I mean, that's fine. Either one in a case like this, it's not really talking to us about having imbalanced data or anything like that. So I guess really either one is fine. Next question, will Google say AUC or area under the curve? Hard to say. My instinct would be they're probably going to say AUC because it's a fairly common, popular acronym out there. But they could say area under the curve. Nothing would really surprise me there. We are going to move on here, and I'm going to hit the various GCP tooling here. This is a pretty meaty section here. So the various GCP tools, you're just going to see so many questions on the exam about, oh, here is a scenario. What's the best tool for it? Like, how would you set this problem up? That's probably, honestly, the most common type of problem. And what it's really getting at is testing over the fundamental different use cases of these tools. I'm going to try and go through these and hit the highlights as quickly as I can. This is every time I teach this course, I get to the fourth hour here, and I literally start losing my voice a little bit. So I'm trying to get on top of that a little bit. But let's start with BigQuery. So BigQuery is one of the absolute most important tools in the entire GCP suite. And a lot of the reason for that is because it's just so versatile. It's one of my personally just favorite tools I've ever used because it just makes everything so easy for you. So it's fully managed. So Google handles all that stuff on the back end. You don't have to worry about compute, storage, or other resources. It's scalable, so it can handle up to the petabyte level of data. Serverless, it integrates very well with Vertex AI, GCP in general. It's optimized for fast data processing and highly cost effective, so it doesn't bill for your unused resources. So it is, broadly speaking, probably the most fundamental SQL tool in the entire GCP suite. And we can also use SQL queries for training machine learning models directly. So let's say you get a question on the exam and it frames it something like, okay, you have a user who wants to go train a machine learning model, but they don't have a lot of machine learning experience necessarily, but they know SQL really well. How should they go about attacking the problem? Well, your answer to that is almost certainly going to be around BigQuery ML. So BigQuery ML basically lets you train all parts of the machine learning process, right? Splitting your data up, training a model, evaluating the model using like the ml.evaluate statement. You can do all of that in BigQuery simply by writing SQL queries. And there's a variety of models possible, like linear, logistic regression, time series models, even up to k-means clustering. I remember the first time I saw it, it kind of blew my mind. Then you got Vertex AI, which is your key go-to for machine learning stuff in general. When I took the exam myself a couple years ago, there was a lot of focus on Vertex AI. And then after that, ever since I took the exam, Google redid the exam so that it could focus even more on Vertex AI. I'm actually not kidding. Vertex AI is really the catch-all for machine learning solutions in the GCP, in the context of GCP. So really for all parts of the process and all different ways of attacking problems. So Vertex AI data sets, feature store. We'll go through a lot of these in more detail, but Vertex AI, Vizier, Workbench and notebooks, model training, Vertex AI pipelines. We'll talk a lot about that later. AutoML is inside of Vertex AI. More recently, again, I'll talk about this in a little bit, but Model Garden for RAGs and agents and all that good stuff falls inside of the umbrella of Vertex AI now. So going a little bit more, so we'll talk about a little bit more of those Vertex AI services later. I'm going to go through here a little bit in terms of just sequentially kind of your process as you go through a machine learning problem, right? So starting all the way from ingesting your data, whether that's batch or real-time streaming data. You have PubSub, which is common approach. That's short for publish and subscribe, where you have asynchronous communication between applications and services. That integrates with services like Dataflow or BigQuery, but just the most important thing to remember with that is that it's ideal for streaming data in real time. You've got DataStream, also for supporting streaming from Oracle and MySQL databases. But also BigQuery offers a data transfer service for migrating data between different data warehouses. So Teradata, cloud storage, AWS or Azure, other cloud platforms. As far as some of these data processing services are concerned, this is another thing. I'm gonna hit 4 of them in my different slides here, but that's critical to know the difference between these, like what the different use cases are. With Dataproc, your use case here really is integration with these Apache things like Spark and Hadoop. So it's a Spark and Hadoop service that allows the user to run big data processing and analytics workloads. So again, it integrates with BigQuery, it integrates with cloud storage, so on and so forth. It's used for these ETL type of processes, batch processing, data exploration, large data sets in general, obviously, because we are working with Spark and Hadoop clusters here. Automating the provisioning, scaling, and management of them. It works for both structured and unstructured data. And again, it is specifically well suited for batch processing rather than real-time processing. So again, Dataproc, think Spark and Hadoop. You have the probably most, if I can get my slot, there we go. You have probably the most popular, common out of all of them, which is Dataflow. So Dataflow is another fully managed service for building and executing these ETL pipelines. Again, it works for unstructured or structured data. It's not really built for integrating with Spark and Hadoop here, but it instead uses a unified programming model based on Apache Beam. It optimizes for performance and cost efficiency by automatically scaling resources based on your workload. It is ideal for processing streaming data in real time, though it can be used for batch or for stream processing. So a little bit more general of a use case. You have data prep, which is a basically more of a no-code type of solution used for visually exploring and cleaning and preparing data. It suggests transformations to the user based on detected patterns. It's UI based, so there's no infrastructure to deploy or manage. Again, it's another serverless and scalable data preparation. There's a reason they call it data prep, right? But you also have Cloud Data Fusion, which again, it's a fully managed data integration service that enables users to build and manage ETL processes in a UI without coding. So it's a completely drag and drop based interface. You make a data pipeline. It uses MapReduce and Spark streaming pipelines. And connectors for databases, storage systems, and software as a service applications, and captures metadata from your data pipelines. No infrastructure management, so on and so forth. As far as some of these warehousing, those NoSQL type of things are concerned, this can be a little bit of a gotcha with these exam questions, because if let's say you need the absolute lowest latency possible solution, again, for these warehousing type of things, that's generally where Bigtable is going to come in. So these are optimized for single lookup operations, like a single row with many columns, and latency can be in milliseconds. So again, Bigtable, if you are truly processing things in billions and trillions and things like that, and you need the highest possible scalability and lowest latency, that's probably going to be your solution. Again, it's for the retrieval of structured data, useful for real-time analytics, like ad prediction, fraud detection, things that need to have serving ads. That kind of stuff needs to happen more in real time. You also have some of these other maybe lesser used solutions. You've got DataScore. That's a NoSQL document database service designed for automatic scaling. It's used for web and mobile applications, metadata storage, user profiles. Or there's Memorystore, which is more of a managed in-memory database, offering high-performance caching, session storage, data caching. Frequently accessed data in memory is going to be kind of your use case there. A few more things I want to touch on before we try some more exam questions. Google likes to ask these questions around, again, I've already said this, but, oh, you need to train a machine learning model. How should you do it? If it asks you specifically about, the user knows SQL, usually that's kind of a hint that it wants you to be thinking about BigQuery. But in general, Google really wants you to go with a pre-trained model first, like if that's even an option. If it's not an option, like there's nothing available for your use case, use AutoML, and if for some reason that doesn't work, then you start going into Vertex AI and training a custom model. So the nice thing with a pre-trained model is it's not something that's going to require coding experience from you or engineering experience. You just use a pre-trained model through an API. It's serverless, so you're not provisioning any cloud resources. You're just consuming this through an API. There's more than I can really possibly go through here, but examples of these pre-trained models like Vision AI, Video AI, Natural Language AI, Translation AI, Speech to Text, Text to Speech, Document AI. Google has already kind of built a lot of these solutions out. And again, the thing I really want to emphasize here is if it's possible to use those, or especially if you're somebody who doesn't have coding experience, that's the first thing they want you to try to look for. Again, I've already talked about these a little bit. Like, it's useful just to know at a high level, like, okay, let's say I want to recognize an object or a place or an action in a video. Okay, Video AI is my pre-trained model for that. You've got a natural language AI, a document AI for extracting info from documents. So just useful things to have in the back of your mind a little bit. But again, just the high level is when do we want to use these pre-trained models versus custom model. You also have AutoML. AutoML, that's, again, it's a service inside of Vertex AI for allowing users to create machine learning models without writing any code. So again, if you don't have a pre-trained solution that's already available, AutoML is the next thing you want to try. And it's good if you have to turn around something very quickly or you have little to no coding experience. It supports structured data, image data, text data, video data. It's very versatile. The data sets are managed by Vertex AI. And again, all these different parts of the machine learning process, it handles. So training models, splitting, hyperparameter optimization, model selection, model evaluation. The list goes on. Let's give me a break from talking. Y'all are probably getting tired of listening to me talk anyway. So again, let's test how much y'all were listening or / awake. Let's try a exam question. Your company deals with real estate, and as part of a software development team, you have been asked to add a machine learning model to identify objects in photos uploaded to your website. How do you go about this? Think about your different options here, and let's regroup in a minute. All right, let's take another 10-ish seconds. 5, 4, 3, 2, 1. Come on, I see a few of you are you're listening, you're on, but you're not taking a stab at this. Make sure you take a stab at it. There we go, a few more in. All right, let's see what y'all thought. All right, 92% of you chose start with Vision AI, and if that does not work, use AutoML, and you are exactly right. Again, if there is a pre-trained model, you want to start with that. And if it doesn't work, then AutoML is the next thing you try. But you always want to start with that pre-trained option if you can. That is the concept here. Next question. The data science team is building a data pipeline for an auto manufacturing company whose objective is to integrate all the data sources that exist in their on-premise facilities via a codeless data ETL interface. What GCP service will you use? Take about 1 minute for this. All right. Let's close this one in 5, 4, 3, 2, 1. Okay. The correct answer here is data fusion. I see the most selected option was data flow. The key here is codeless. So data flow is not a codeless solution. When you see codeless, it's really going to be between data prep and cloud data fusion. Those are kind of your two more codeless based solutions. Then a distinction here between them is that if we're building a more complex, like ETL-based data pipeline, cloud data fusion is going to be your go-to. Data prep is a little bit more for like just visually cleaning and preparing data, but it's a little bit more of a interactive kind of simpler like data exploration and visual data preparation tool as opposed to a data pipelining sort of tool. So cloud data fusion is our correct answer here. There's a few more questions I want to get through, and then we'll take a break. You are a data scientist working on a smart city project to build a machine learning model to detect anomalies in real-time sensor data. You will use PubSub to handle incoming requests. You want to store the results for analytics and visualization. How should you configure the below pipeline? We already know we're ingesting data using PubSub, but then we want to pre-process, then we want to do machine learning training, then we want storage, and then we want visualization in, it's an older question. We would probably do visualization in Looker, but Looker, Data Studio, doesn't matter. Let's take a minute on this one. All right. Let's close this one in 5, 4, 3, 2, 1. Okay. The most common selected answer here, Dataflow, Vertex AI training, and BigQuery, that is correct. So I think we all get the idea here that we want to use Dataflow for our pre-processing needs. That's kind of what it's for. Machine learning training we can handle through Vertex AI training service. With storage here, that's a key. That's really the key distinction here, because when we want a visualization layer on top of whatever it is we're trying to do, BigQuery it just integrates really well with all of these other Google's GCP services. So that's really one of the big distinctions here. You want to store your data. And it also integrates with Vertex AI, right? So if you want to go back and forth seamlessly between anything that's happening in Vertex AI and any kind of visualization layer, BigQuery just makes that as seamless as possible. So that's why this answer, this top one with Dataflow, Vertex AI training, and BigQuery is the correct one. We're going to do 2 more questions, and then we're going to break. Here's another similar one. You are a data scientist working on a fraud detection model. You will use PubSub to handle incoming requests. You want to store the results for analytics and visualization. How should you configure the following pipeline? We ingest data, then we pre-process, and then we do machine learning training and visualize in data or Looker Studio. Think about that for a minute, maybe a minute and a half, and then we'll go over it. Take another 10 seconds or so. 5, 4, 3, 2, 1. All right, I saw a little batch of predictions come in there, or batch of answers come in there. Let's see what y'all thought. Okay. There's actually a tie with what y'all selected here. The answer is PubSub followed by Dataflow followed by BigQuery ML. So again, it's a similar kind of concept to what we were going over in the previous question, which is around BigQuery just really integrate. Just number one, BigQuery can handle your ML training, but also it just integrates seamlessly with data or Looker Studio. That's kind of why we want to use BigQuery ML. Now, it's important to know the distinction here as well as far as ingesting versus pre-processing data. For ingesting data from source, that is a PubSub task. When you're pre-processing the data, that is a Dataflow task. So Dataflow is for pre-processing the data. Once we start machine learning stuff, that is generally when Vertex AI is going to come in. In this case, you don't really even need to go to Vertex AI. You do pub sub for ingesting, Dataflow for pre-processing, and then BigQuery ML for, well, that can handle your machine learning needs here, as well as moving on and storing it so that then you can go for visualization. All right, last but not least, before we break, you are training a TensorFlow model on a structured data set with 100 billion records stored in several CSV files. You need to improve the input and output execution performance. What should you do? Let's think about this for a minute or so, minute and a half. By the way, I might have forgotten to mention, but as we're going through this, keep track of how well you're doing on the questions. It will provide you some kind of measure of how ready you are, and it's just good for your sake just to have some kind of scoring at the end. Like, oh, did you score 30%, 50%, 70%? Just measure your performance here. I'm going to close this question off in about 10 seconds. Let's go. 5, 4, 3, 2, 1. All right. Okay, this makes me happy. All right. The majority of y'all picked the correct answer, which is loading the data into Cloud Bigtable and reading the data from Bigtable. I'm just going to say, when I was prepping for the exam, I remember seeing these questions, and I got this one down, and then I literally saw a question almost exactly like this on the actual exam. Your experience may or may not vary. I really have no idea. But just saying, I saw a question just like this on the exam myself. The key here is 100 billion records. That is a ginormous, and we want to improve latency and performance. So the absolute lowest latency type of solution is going to be Cloud Bigtable. That is really our key here, is that we have such an enormous number of records, and Bigtable is designed for low latency reading of such a large number of records. I'm going to give us a break here. Take about 7 minutes. I'm going to get us back up and going at about 5 after the hour. It is 7:58 in the morning my time, so it will be 8:05 my time. But again, just 5 after the hour, about 7 minutes. Take a bathroom, coffee break, whatever you got to do. I will come back every now and then and check the Q&A. Break, and then we'll talk about feature engineering. All right, let's get started again here. I lied and said we were going to start at 5 after the hour, and well, I wanted to take a little bit more break myself, so I gave that to all y'all as well. The next topic that we're going to go through here is around feature engineering. This is a bit of a smaller kind of subsection that I've kind of, again, kind of subsection, just kind of made it its own thing. Google definitely likes to ask a question here and there about this, so it's just good to have this in your back pocket. They have a lot of good, like on Cloud Skills Boost, as well as in any other resource you go to. There's a lot of good documentation on this. So I'll try to hit the major highlights that they'll want you to know. Starting with what is feature engineering? It is essentially the process of determining which features might be useful in training a model and then manifesting those features, creating them by engineering or transforming your raw data. So again, determine which features might be useful in training a model, convert the raw data from the data set into different versions of those features. Remember, models need vector or numerical representations of features to perform mathematical computation. So the most common stuff you see here with numeric data would be, for instance, normalizing. That gets particularly important with things like neural networks because those are very much not scale invariant in the training process. Something like trees, for instance, that's less of a problem, but I digress. So normalization is transforming numeric data to the same scale as other numeric data. Again, you may need to do this because of model performance issues, and also speed issues, so convergence. Bucketizing can happen where we transform numeric data into categorical data. There's all kinds of different use cases when one might want to do that. Like maybe we want to create buckets with equal spaced boundaries. Those boundaries are based on our understanding and knowledge of the problem, or you want to create buckets with quantile boundaries. That's another pretty common approach. Similarly, with transforming categorical data, the most important application of that is one-hot encoding. That's where, for instance, instead of having, let's say, as a categorical variable and the values of that variable are like red, green, or blue, instead, and that's your only three options. Instead, we would turn that into three new variables or three new columns. It would be like color red. This would be like 1 if it's red, 0, the green is 0, blue is 0, so on and so forth. It's basically transforming the levels of that variable into their own columns. You also have feature hashing as a interesting one for applying a hash function to categorical features. And now embedding, that's one to just, the exam is not going to test you on all of just the total ins and outs of things like embedding, for instance, but representing a categorical feature as continuous valued, it's obviously that's the basis of anything in the natural language processing, LLM world, text and document classification. So the use case of that kind of stuff is the most important thing to have down. As far as feature selection is concerned, we'll do that for selecting a subset of features. So you'll often want to do that so that you maintain only the features which are the most useful for a model in order to predict the target. Why would you want to do that? Reducing noise from data, because the more columns you have, you risk overfitting. You might want to reduce the training time and your use of computational resources. And in many instances, it'll outright improve the performance of many machine learning algorithms. I guess that's in some ways that goes hand in hand with overfitting. When you're not overfitting, you're going to improve your performance on unseen data. But it fits into our broader conversation here because we want to select only the most important features or create combinations of new features. A very important way, and when I say important, specifically in the context of what Google likes, is feature crosses. So with feature crosses, those are synthetic features formed by crossing categorical or bucketed features. So I like this example because it really illustrates the concept nicely. So suppose you're predicting housing prices for cities in California. So we want to predict house sale prices based on the house location and rooms per person. Location is this very nebulous type of variable. Like, how do you even go about representing that? Obviously, you can do that by latitude and longitude, but does it really make sense to go represent latitude and longitude in these super continuous ways? Maybe, I don't think so. So the approach we could take here would be measuring that with binned latitude and binned longitude. So sort of transforming the latitude and longitude and making them categorical, because those categories inherently are going to mean something a lot more relevant. So what you could do here for creating a new feature is to create this feature cross, like binned latitude times binned longitude times rooms per person. And that way the model could possibly learn city-specific, neighborhood-specific, or even block-specific effects. And rooms per person could be totally different of an effect based on what location you are. And we can really get that location effect down by bending these things and then making the feature cross so we can capture how all these things interact with one another. There's good resources out there for this too on Google's documentation. A couple more things before we try a few exam questions. Google wants you. It's a lag and pushing to the new slides here. There we go. Google wants you to know the various TensorFlow functionalities and these TensorFlow services. So just again at high level sort of stuff. This is not a coding exam, but knowing what at a very highest of level the different TensorFlow utilities will serve you quite well. So starting with the TensorFlow Data API, that provides us a set of Python functionalities under this tf.data module. Specifically with the key is the dataset objects. So what can we do with it? Prefetching transformations using the dataset.prefetch method, caching data in memory using the dataset.cache method, parallelizing your data reading with the dataset.interleave method. Most importantly, it can handle various data formats like TensorFlow records or TF records, CSVs, or image data. You've got TensorFlow Transform, which is part of the broader TensorFlow extended suite. So this will allow you to define your pre-processing steps at training time that can be applied consistently at inference time. This is a very important point. You can perform transformations prior to training and during. So to avoid training and serving skew, you can ensure the same transformations are applied both at training and at inference time. So Transformations could be analyzing and transforming training data, transforming validation data, producing metadata, serving data. And you can integrate this with Apache Beam for processing larger data at scale. So again, these TensorFlow questions, just know what these services are there for, what these modules are there for, what you can do, because it falls under the broader umbrella of things Google wants you to know around feature engineering. One last just point, and then we'll try a few exam questions. Vertex AI provides us a feature store service. So that's a fully managed, centralized repo within Vertex AI for storing, sharing, and managing features across various models. And so when you go train a model, the users can define features and import them from other sources. You can retrieve them in real time if you want to do like real-time predictions. And just the idea here is it just cuts down on just redoing a lot of this work across different models, across different projects. Just gives you a single source of truth for all machine learning features. And we already know this about Vertex AI. All these services integrate with each other and just sort of flow in and out of each other really nicely. Let's do 2 exam questions. Give me a break from talking. All right. I say that as I start talking the question out. You're the data scientist for your company. You have a data set which has all categorical features. You trained a model using some algorithms. With some algorithms, this data is giving good results, but when you change the algorithm, the performance is getting reduced. Which data transformation strategy would likely improve the performance of your model? Take a minute or a minute and a half. Let's take 15 more seconds. All right, I'm going to close this one in 5, 4, 3, 2, 1. I see the response rate dropping off just a little bit, so hope you all came back from the break. But get your answers in if you haven't. Okay. The correct option here is actually using one-hot encoding on all categorical features. A key here is that some models can handle categorical data, and that tends to not be a problem. But for some algorithms, they simply require these things to be encoded that way, or they just work better with numerical data more generally. So one-hot encoding is our solution for converting our categorical features to numeric. So that's the thing that we want to make sure that we do when we have all categorical features like this. One more question. You're transforming a complete data set before model training. Your model accuracy is 99% in training, but in production, its accuracy is 66%. What is a possible way to improve the model in production? Take about a minute or so on that. Take another 10 seconds or so. 5, 4, 3, 2, 1. Okay. Our correct answer here is use TensorFlow Transform for creating production pipelines for both training and serving, because what we're looking at here is probably a case of training serving skew based on our discrepancy here. I don't think data normalization is necessarily going to like. You're probably, if that wasn't being done, you're probably not going to have accuracy like that during training. I wouldn't think so. So yeah, this is that's kind of the concept I was mentioning earlier, that TensorFlow Transform provides us some ways that we can make sure that this sort of problem, this whole discrepancy between the accuracy during training and during serving and production, making sure we don't have a skew or a discrepancy one way or the other there. All right. So moving on to all things model building, training, tuning. We've already talked a lot about evaluation, but a little bit more about less so the human evaluation of these models and more so loss metrics and training and things of that nature. A couple things. So, got a lag there. Modeling techniques. This is an important one to know the difference between. We'll talk as we go through the rest of this course. There's a few more specific ones that I'm going to bring up, which will be more relevant to the specific type of content that I'm talking about then. But this is an important one, the distinction between convolutional neural networks and recurrent neural networks. So the key to know here is convolutional neural networks are designed for image input and image classification. Recurrent neural networks are designed to operate on sequences of data. Now, sequences of data, that's a little bit more broad of a use case than you might be used to thinking of at first. Like, it's not just necessarily over time series data. Recurrent neural networks are common for natural language processing problems, because a whole foundation of those types of problems is, okay, you have a word. Well, what's the next word? Well, what's the next word after that? It's sequential. So that's an example. You've got one very classic example of this is the long short-term memory network, LSTM network. That's a very popular type of recurrent neural network. So cost functions. So your cost function is going to quantify how much error the current model has. So how is that done in terms of selecting a model here? Well, with regression problems, it's typically they use mean squared error or mean absolute error. With binary classification, there's binary cross-entropy, categorical hinge loss, or squared hinge loss, if that's a Keras use case. For multi-class classification, we can use categorical cross-entropy if one sample can have multiple classes or labels, or sparse categorical cross-entropy if the classes are mutually exclusive. That is, one sample can belong to exactly one class. Are y'all awake? Y'all paying attention? Hope so, because we got exam questions next. All right. Your team needs to build a model that predicts whether images contain a driver's license, a passport, or a credit card. The data engineering team already built the pipeline and generated a data set composed of 20,000 images with driver's licenses, 2,000 images with passports, and 2,000 images with credit cards. You now have to train a model with the following label map: driver's license, passport, credit card. Which loss function should you use? Let's think about that for a minute or so. All right, take another 10 seconds. Four, three, two, one. It's a 50-50 split between categorical cross-entropy and sparse categorical cross-entropy. So the correct answer is sparse categorical cross-entropy. Nobody selected the first two options. Those are for binary classification problems. This is not that. It's a multi-class classification problem. The key here is that our labels are mutually exclusive. So for instance, if I go, we go look at an image, that's either a driver's license, a credit card, or a passport. A driver's license can't be a credit card. A credit card definitely can't be a passport. So these things are mutually exclusive. So if they aren't, you can go with the regular categorical cross-entropy. If they are mutually exclusive, you go with the sparse version. This next one should help keep you on your toes a little bit here, because it's a little bit more thematically related to topics that we've been talking about, not necessarily in the last 5 minutes, but within the broader course so far. You work for a bank and you're building a random forest model for fraud detection. You have a data set that includes transactions of which 1% are identified as fraudulent. Which data transformation strategy would likely improve the performance of your classifier? Take just under a minute on this one. Let's take another 10 seconds. 4, 3, 2, 1. Got your answers in? You sure? All right. Oh, wow. We definitely have a little bit of a spread here. The correct answer is oversample the fraudulent transaction 10 times. So this here is a classic example of imbalanced data. So 1% of the data are in one class, that's fraudulent transactions, and 99% are non-fraudulent. That's very common in fraud detection problems. Matter of fact, in real fraud detection problems, it's probably worse than this. Oversampling is our technique for dealing with that sort of problem. Key here is we just talked about all this TensorFlow records and normalization, one-hot encoding, and all that stuff, all that feature engineering stuff. But I wanted to keep you sharp here, so threw in a question about just how you handle these problems a little bit more broadly here as we start going into this much more broad machine learning section here, model training and all that good stuff. Okay. So it's critical in general anything in the machine learning ecosystem, but that also extends to this exam to understand the trade-off between bias and variance. So when we're underfitting, we generally say that the model has high bias and low variance. The model is too simple, and so on. With overfitting, which is definitely the more common of the two, at least I think. Overfitting, you're fitting the training set very well, but poorly generalizing to new data. That is, we can say the model has low bias, but high variance. Ideally, you want to fit the training data well, but you can't be fitting it so well that it does not generalize to new unseen data. That's kind of the trade-off that we always run into here. There's a lot of solutions for overfitting. I mean, we talked about feature engineering and feature selection, which that's one method, but a couple others I want to talk about here are early stopping and regularization. Those are important concepts. So for early stopping, for this, you need a validation data set. So sometimes you'll see the way that data gets partitioned off. Sometimes it's just a training and a test set. Sometimes it's a training, validation, and testing data set. It just depends on a variety of factors, like how much data you have, how much you're really willing to use for a validation set, but you need a validation set to do early stopping. The idea here is we end training before the training loss finishes decreasing. So we're stopping the training when we see the loss on a validation data set start to increase. That way we can ensure that we ideally have the best performance possible on the test data, so on unseen data in general. So again, the whole concept why you might want to do that in the first place is it's just a tool we have in our toolbox for diminishing our chances of overfitting. Then you've got regularization. That is somewhat broad in the sense that it's just any method that reduces overfitting, and it's done by assigning a penalty on the model's complexity. Again, the more complex the model, the higher variance it's generally going to have. The more complex the model, the more likely it's going to overfit. So can't stress it enough, you want the model just complex enough to where it learns the data well, but not so complex that it doesn't generalize to anything. So we already talked about early stopping, but the other popular types of regularization include L1 regularization and L2 regularization. It is critical to know the difference between these two and just what they're doing, what's the basic difference between them, what's the trade-offs. This is critical. Like, I would be shocked if you go and take the exam, and there's not a question about this. So L1 regularization. Well, that adds a penalty. This is also known as the lasso. This adds a penalty equal to the absolute value of the magnitude of coefficients to the loss function. The most critical distinction with L1 regularization is that it can zero out some of the model weights. So what you're doing is it's essentially saying, well, we're going to make this feature worth 0. So it essentially all it's doing is performing feature selection. It can literally do feature selection, just drop these things out completely. And it's also robust to outliers. So with L2 regularization, that's not the case. So for some reason, you want to preserve all the features that you have in data as you go train your model, but also want to minimize overfitting risks. You're going to go with L2 regularization over L1. Or this is the other big use case for L2 regularization. If you want to help with multicollinearity concerns, so it tends to shrink the coefficients relatively evenly and proportionally to each other. It does this by adding a penalty equal to the square of the magnitude of coefficients. So it's very useful as we try to improve the generalization of linear models. But key things here, if you take one or two things away from this slide, L1 regularization can drop features. L2 regularization doesn't. That's its specific use case is generally more, it's more useful in specific cases where multicollinearity is a concern. Another concept here that, again, it's just another one of those things that I would be just shocked if the exam doesn't test you on, is data leakage. This is common. I've done this myself. So data leakage is a situation that occurs when the model has been exposed to the test data during training. Just in some way, your model's cheated and it's learned something about the test data. The most common way that happens is you start performing operations on the data, like normalizing, and anything like that, before we split and do training, testing, and validation sets. So sometimes it can happen. You make the target variable a feature by mistake. This can happen with time series data if you're splitting randomly rather than sequentially, because the model can learn things about the past because it's seen the future data. That's another way this could happen. Again, just make sure the very first thing before you perform any sort of pre-processing operation is splitting the data into training, validation, and testing. That is the first thing you want to do. We'll talk very briefly here about hyperparameter tuning. Let's see if I can change my slide. Sorry, just a second here. Sorry, we're running into a little technical difficulty here. Brittany, if you're on, can you move the slide?
Yes, which side would you like?
Let's switch to, oh, there it went. Yeah, thanks for that. It was stuck for some reason. I don't know if it's on my end or what it is. Okay, so hyperparameter tuning, what is that? Basically, we're trying to find the best version of a model by running many training jobs, utilizing the algorithm and a specified range of hyperparameters. A hyperparameter is an external configuration of the model that is not learned from the data, but is set prior to the training process. It requires manual specification, and it's not something that you can just a priori just know, oh, that's going to be the best hyperparameter. It's something where you kind of have to go through this process in order to find the one or ones that are the best performing. So moving to our next piece here, Vertex AI offers a service for a hyperparameter tuning. That's Vertex AI Vizier. That is a fully automated hyperparameter tuning and optimization service where a lot of these options are laid out for you very nicely there. So it automates the process, allows you to define a search space for hyperparameters, use algorithms like Bayesian optimization, random search, and grid search, parallelizing hyperparameter evaluations. Obviously, any of these Vertex AI services integrate very well with each other, but it also provides cost-aware optimization strategies. So like, for instance, Bayesian optimization is the most cost-effective of all of these. Grid search is the least cost-effective because you're literally going through an entire grid of all these different combinations of different hyperparameters. But also intelligently scheduling trials, dynamically adjusting parallelism, early dropping of unproductive trials if we're not getting anywhere. Oh, there we go. So some of these last metrics, these are just a few things we'll go through here before we get into the a few more exam questions. We'll just cover these last things, and then we'll around training metrics here, and then we'll do some exam questions, and then break. Your batch size is the number of training samples used in one iteration of model training. It is absolutely critical to understand how this is going to affect model training as we increase or decrease it. So if we have a smaller batch size, that is going to lead to faster convergence as the model is updated more frequently, but it's going to cause higher variance in the training performance. If you have a larger batch size, so a larger number of samples that the model is exposed to before we update the model's weights, you're going to get more stable estimates, but it's going to require more memory, and it's going to slow the whole training process down. Talking about epochs. So epochs is the number of times that we run through the entire training data set. So if a model has seen every sample in the data set once, it has completed one epoch. So epoch, I've heard different pronunciations of this word over the years. Fewer epochs can prevent overfitting, but it might result in underfitting because the model hasn't learned enough from the training data. So really, this is all about underfitting versus overfitting type of risk. Fewer epochs, you're running more of an underfitting risk. More epochs, you're running more of an overfitting type of risk. And then talking about learning rate. So learning rate is the size of the steps that the model takes during optimization, say during that whole gradient descent process. So if you have a lower learning rate, you're taking smaller steps. So the lower learning rate, you can get more stable convergence, but it can make the training process slower and potentially get stuck in local minima. With a higher learning rate, the model will learn faster, but the loss function will tend to oscillate wildly all over the place. It can lead to unstable training or divergence. Right. We have 4 exam questions that I've queued up here, and then we'll go to our next break. Sound good? I know there's some questions that came in, but let's get this next question started here. You are a data scientist training a deep neural network. During batch training of the neural network, you notice there is an oscillation in the loss. How should you adjust your model to ensure it converges? Take a minute or so on that. Let's take another 5 seconds here. Let's go 5, 4, 3, 2, 1. I know there was a question in the chat about using a grid search CV for auto tuning of hyperparameters. I don't think it's using grid search CV necessarily, but any kind, like you have your grid search, your random search, your Bayesian optimization. Those are the kind of the most critical methods, but it enables all of those. On this question, the correct answer is decreasing the learning rate hyperparameter. So the key here is around oscillation in the loss. When you see that, that is generally because the learning rate is too high. So if you decrease this, it should stabilize the learning process. In general here, you want to be a little bit careful about increasing and decreasing your batch size because increasing the batch size might diminish your accuracy. Decreasing it can increase loss oscillation potentially. Generally, this kind of thing, your first go-to here is probably going to be decreasing your learning rate hyperparameter. See if that works and then go from there. Moving on to our next question. You started working on a classification problem with time series data and achieved an area under the receiver operating characteristic curve value of 99% for training data after just a few experiments. You haven't explored using any sophisticated algorithms or spent any time on hyperparameter tuning. What should your next step be to identify and fix the problem? Yeah, we don't believe 99%. That's usually not real. So let's think about this for about a minute and a half. Let's take another 10 seconds or so. All right. Let's go. 5, 4, 3, 2, 1. Okay. This is one of the trickier ones. The answer here is address data leakage by applying nested cross-validation during model training. So we have a problem here with data leakage. The issue here is not overfitting. Because overfitting, that's where we'll have really good performance on our training data, and then we see it drop off when we get to the test data because the model isn't generalizing. This is more of a data leakage type of problem, where somehow it's learned the outcome variable. Just in and of itself, having features that are highly correlated with the target value is not a problem. In fact, that's generally how the model is going to learn the target the best. Even if the model is as perfectly designed as possible. Nested cross-validation is just a pretty common technique that we can use for getting around the data leakage issue. So again, this is the key here is data leakage is our concern and our problem here. Nested cross-validation could just be a way that we attack that, but we don't need to remove things that are highly correlated with the target value because that's just going to needlessly drop the performance. Next one, you need to write a generic test to verify whether deep neural networks models are automatically released by your team have a sufficient number of parameters to learn the task for which they were built. What should you do? Let's take a minute on this. Take another 5 to 10 seconds. All right, saw a little batch of answers come in there. Closing this one in 5, 4, 3, 2, 1. Okay. The plurality choice here is the correct one. We'll train the model with no regularization and verify that the loss function is close to 0. And the idea here is if we've trained the model so that it has enough hyperparameters to learn this job, the loss function should decrease. It should get progressively closer to 0. Outperforming a linear model doesn't necessarily mean that we have enough parameters to learn tasks, particularly if our relationships between our features and our target have nonlinear representations. All right, one last question, and then it's time for the break. Oops. Your training, validation, and test sets have similar distributions. You've subselected the most relevant features and trained a neural network in TensorFlow. TensorBoard plots show the training loss oscillating around 0.9, with the validation loss higher than the training loss by 0.3. You want to update the training regime to maximize the convergence of both losses and reduce overfitting. What should you do? Let's think about that for 1 or 2 minutes. Let's get your best guess in here. I want to close this one soon to make sure we have enough time for a nice longer break here. Take another 10 seconds. This one is a little, and I understand it because this one is just wordier. Take another 5 seconds. 5, 4, 3, 2, 1. Y'all get it in? All right. The solution is, oh, wow. The correct answer is introduce L2 regularization to fix the validation loss. In general, these answers with increasing the number of epochs, that could actually make the problem worse, right? Because increasing epochs could increase our chance of overfitting here. So don't add a whole bunch of other stuff onto this. What we want to do, and similarly with increasing the learning rate, that's not expected to fix an overfitting problem. Our best solution is keep it simple. Just introduce L2 regularization. I suppose L1 regularization would work too. I haven't seen anything in this question which indicates that that wouldn't be an option. But again, there's no reason to do all this other unnecessary stuff. Just regularization by itself, and we'll start there. All right, let's break. It's 2 minutes after the hour now, and let's come back together at 10 after the hour. in general, I haven't done the greatest job this time of calling this out, but as you have questions or things you'd like to learn a little bit more about, feel free to leave those in either the Q&A or the attendee chat, and I will try and get to them as best I possibly can. But yeah, let's go ahead and get started here on the back half of this course. So I want to talk a little bit more about TensorFlow. As we go into this next section, we're going to talk a lot more about the hardware, right? We've talked already a lot about these back-end services, what you're doing with your data, like what service do you use for this kind of use case, what's the difference between them, all this model training stuff. But what about the actual hardware? Now, I've never worked at NVIDIA. This is when I was learning this stuff. This was the content that I had to kind of learn myself the most as I was going along. We'll get to the distinctions later between training strategies, CPUs, GPUs, and all that stuff. But I want to spend a little bit more time on TensorFlow to make sure that gets the attention that it deserves. What is TensorFlow? It's an open source machine learning framework that was developed by Google for building and deploying machine learning platforms. So it can be used for users can build and customize their own machine learning models for all kinds of different use cases. We'll talk a lot more about these things in the next few slides here, but it supports distributed computing across CPUs or GPUs. It's optimized for performance. Again, we can use things like GPUs and TPUs to bump that up. It includes TensorBoard, which is we talked about that in one of the last questions, but it can visualize some of these and monitor these models and training metrics. It's widely used for deep learning tasks and natural language processing tasks. Talking a little here about CPUs and GPUs. Yeah, this is a big one. So CPUs are versatile and suitable for general purpose computing tasks, rapid prototypes, or models that train fast, and they're more cost effective. So if you have concerns over cost, you might not want to jump directly into using a GPU. But they're not necessarily optimal for latency sensitive tasks or for parallel processing. GPUs are designed for highly parallel processing tasks and can accelerate the training process, but again, they're more complex and difficult to manage. Developers sometimes need to write code that's specifically optimized for GPU architecture, and they're more expensive. If you have custom TensorFlow operations, GPUs are a great resource. Remember that. If you've written your training code to use GPUs, then you can configure your worker pool to use one or more GPUs. If you just go look at some of the resources on this, like the compatibility, there's just a couple things I'll point out in a little bit here. You do not have to go and memorize these tables. Please do not do that as you go study for this exam, or you will be wasting your time. One of the important things to highlight here is that you must use an A2, N1, or G2 machine type. Those are the only machine workers that are going to be compatible with GPUs. Just a few more GPU constraints to note here. In your worker pool spec, you specify the type of GPU you want to use and the number of GPUs you want to use. The type of GPU must be available in the location where you're performing custom training. That's important. This one is a good one. you have limitations, and we'll look at a table on this in a second, but you have limitations on the number of GPUs in your configuration. So for instance, you can never use 3 GPUs. You can use 2 or 4 NVIDIA Tesla T4 GPUs on a VM, but not 3. There's no configuration that I'm aware of where you can use 3. And you must make sure your GPU configuration provides sufficient virtual CPUs and memory to the machine type used. So this may become clear as we start working through a few of the exam questions we'll do. But for instance, if you're using the N1 standard 32 machine type in your worker pool, each VM has 32 virtual CPUs and 120 gigs of memory. Well, since each NVIDIA Tesla V100 GPU can provide up to 12 virtual CPUs and 76 gigs of memory, you would have to use at least 4 of those GPUs for each N1 standard 32 VM to support its requirements. If this is all a little abstract to you, it is useful just to go stare at the table on this for a little bit. Again, don't go memorize this because you really don't have to go to that level with this. But in particular here, you'll notice with some of these machine types, they're compatible with maybe 1 GPU, maybe 2, maybe 4, maybe 8, maybe 16. It's never like these odd numbers like 3 or 5 or 7. It's always like 1, 2, 4, 8, or 16 GPUs. That's an important thing to remember. If you remember that the GPU has to be available in your region, that's important. And then again, N1, A2, G2 machine types. That's another important point here. You know those things. You're probably going to be in pretty good shape as far as some of this GPU stuff is concerned. And the fact that GPUs are applicable for when you have custom TensorFlow operations. So talking a little bit about TPUs, these are custom built by Google for machine learning workloads. They're specialized and primarily used for them and have outstanding performance in deep learning, but they are not suitable for general purpose computing tasks. You should know what an edge device is too. Those are used for performing computing tasks at or near the data source. It's good for reducing latency and bandwidth requirements. They're generally just customized for specific use cases, and they have limited computing resources compared to cloud-based solutions. As far as a little bit more about TPUs here, you can use a single TPU or a TPU pod, which would be a group of TPU devices, a TPU slice, which would be a subdivision of a TPU pod, or a TPU VM. What I will say is, this is probably the most important takeaway here. TPUs can be dramatically faster than GPUs, and especially CPUs, but they are not suited for cases with custom TensorFlow operations, or if you have a lot of frequent if-else conditional branching or sparse data with few non-zero values. A little bit on this. TensorFlow Enterprise versus TensorFlow Extended. You should know just broadly what those things are. These are offerings from Google related to machine learning, but TensorFlow Enterprise is a service offering from Google Cloud designed to offer enterprise-level support for TensorFlow. So Google Cloud support, service-level agreements, support for deploying and managing TensorFlow in production environments, versus TensorFlow Extended, which is an end-to-end machine learning platform for building, managing, and deploying ML pipelines. So you've got all the different components inside of that for data ingestion, feature engineering, model training, ML ops, layers, all that good stuff. I'm going to do one more slide here, and then we're going to go to questions. Distributed training. So this is another one where you're going to need to know the difference between all of these. to do this, you can and specify what you want to do. You can use the TensorFlow distribute strategy TensorFlow API to distribute training across multiple CPUs, GPUs, or TPUs. So what's the mirrored strategy? That is designed for synchronous training on multiple GPUs on the same machine, as opposed to multi-worker mirrored strategy, which extends the mirrored strategy to multiple machines, often which each of those machines have multiple GPUs themselves. That's typically the case. TPU strategy would be designed for synchronous training on multiple TPUs, and parameter server strategy would be designed for asynchronous training across multiple workers. Some of those machines would be designated as workers and some as parameter servers. So if we have a use case for large scale models and data parallelism, that would be applicable. All right. I am going to hit you with 5 exam questions now. Again, these hardware questions, this is a big component of the exam, so it is critical to have this stuff down. Distributed training strategies, hardware, this stuff is very important to know on the exam. If you know this, you're going to be in a great position. Let's see how much you're paying attention. You're working for a startup on several projects with TensorFlow. You need to increase the performance of the training, and you are already using caching and prefetching. You want to use a GPU for training, but you have to use only one machine to be cost effective. Which of the following TensorFlow distribution strategies should you use? Let's take 45 seconds on this. Let's take another, the response rate is slowing down a little bit here. Let's take another 10 seconds or so on this. All right, I'll close this one in 5, 4, 3, 2, 1. The majority answer here is the correct one. So our correct answer is mirrored strategy here. Keys with this one are that we want to use a GPU, we don't want to use a parameter server or a TPU, and we want to use only one machine. Remember, with a multi-worker mirrored strategy, we're going to be extending to multiple machines, but a mirrored strategy, that's only applicable to one. I saw a TPU strategy question in the Q&A. Is it on the same machine? It could be. It depends on your setup. You can use one machine or you can use multiple machines for a TPU strategy. That's not going to be applicable for this particular question because we specifically do want to use a GPU. I also saw a question come up about is an edge device a type of ASIC. I don't believe so, no. With an edge device, I think you can include ASIC in the setup, but it's not a type of ASIC. Let's push here. Your team is building a CNN for an image segmentation problem on-prem on a CPU-only machine. It takes a long time to train, so you want to speed up the process by moving to the cloud. You experiment with VMs on Google Cloud to use better hardware. You do not have any code for manual placements, and you have not used any custom transformations. What hardware should you use? Take a minute on this one. Let's get those responses in, y'all. Make sure you're participating in this. It's good because you'll just measure how well you're doing. Measure how ready you are for the exam. Take another 10 seconds. All right, let's go with 5, 4, 3, 2, 1. Okay, wow, this was all over the place. All right. The correct answer is a VM with 1 TPU. A few things here. The N1 standard 2 machine is actually too slow for it doesn't support GPUs. It's too small for GPUs. Next option with the high CPU 16 machines is not really solving our problem because we're still using CPUs and we're trying to move up in hardware here. So the TPU option is probably going to be better than GPUs here because we're not using manual placements and we're not using custom transformations. Manual placement being when we have to manually configure, do we want to use a GPU or a TPU? What hardware do we want to use versus Google kind of automatically handling that for us on the back end. So so TPU is what we want to do here. If we were using custom transformations, and TPUs would not be appropriate. But remember this point about custom transformations. That's very important. You are training a deep learning model for object detection. It is taking too long to converge, so you are trying to speed up the training. While you are trying to launch an instance with a GPU, with a deep learning VM image, you get an error that the NVIDIA Tesla V100 was not found. What could be the problem? Take 30 to 45 seconds on this one. Let's make sure you're getting your answers in. It's fun for me and it's great for you guys too, I hope. All right, let's close this one in. Let's give 5 seconds. 4, 3, 2, 1. All right. The error here is the first one. The GPU was not available in the selected region. This one should hopefully be pretty self-explanatory. If it's not found, it's not there in your region. GPU does have to be available in your specific cloud-based region. You're building a product that will accurately throw a ball into a basketball net. This should work no matter what is placed on the court. You've created a very large TensorFlow model with size more than 90 gigs based on thousands of hours of video. The model uses custom operations and it has optimized the training loop to not have any I/O operations. What are your hardware options to train this model? Let's take a minute on this one. All right, we'll close this one in 5 seconds. 5, 4, 3, 2, 1. Get your answer in. All right. Ooh. All right, the correct option here is use a GPU-only instance. So not a lot of you got this one right, but this is use a GPU-only instance. And the reason for this is because we are using custom operations. So let's say, for instance, I don't know, just making something up. You want to make up your own loss metric, and you have to define a function which isn't available in standard TensorFlow library. You're doing something like that. That's just an example of a so-called custom operation. TPUs are not appropriate for that kind of situation. Nobody selected the CPU-only instance because we want to level up our performance and speed here, because this is a very large model with 90 gigs with thousands of hours of video. So the only thing that's going to work here is our GPU-only instance. Let's do one more exam question. That is, you want to use GPUs for training your models that need about 50 gigs of memory. What hardware options do you have? Let's take a minute on this one. Let's take another 10 seconds or so for this one. Close this one off then. 5, 4, 3, 2, 1. Okay, the majority got the correct one here. The only option that's going to work here is the N1 standard 64 with 8 NVIDIA Tesla P100 GPUs. For this one, you have to know some of the high-level constraints here. So this is, again, to my point of you don't need to go memorize the whole like messy table. It's not that serious, but just know some of your highest level constraints here. So for instance, N2D and E2 devices, those instance types do not support GPUs. You need to be using an A2 or an N1. And none of these instances support 3 GPUs. So that option for option 3 with the 3 NVIDIA Tesla P100s, that's never going to be the case. You want the N1 standard 64. That's going to give us enough memory for the 50 gig memory requirement that we have here. N1 is a machine type that's going to support GPUs, and 8 is a valid number. That's not even something that I remember off the top of my head, to tell you the truth. But I can tell you 3 is going to be a no. Is going to be a no-go. So it's a process of elimination and ruling things out versus violating some of our important constraints here. All right, a little bit more that I want to talk about, then we will do exam questions, and then we will break. Just a few more slides to go over here. Batch versus online serving. We've already kind of touched on this a little bit in some of the earlier content, but an ML model can provide predictions in two ways: offline or batch prediction, or also online prediction, which would be more of a near real-time sort of situation. So the distinction here is collecting the data over a period and then processing it in a single batch. So something like a demand forecast, it's not a historical analysis. If computational resources are limited or cost is a concern, then you would want to design the problem as a batch prediction type, versus online prediction, where these things are happening in near real time as the data is received. The model is always running 24/7 and the predictions are made on demand. I used to work in the ad tech world where we used real-time bidding systems, or recommendation engines are another use case. Fraud detection needs to be happening pretty much all the time. Dynamic pricing. These are all kind of applications of that. We'll have to touch a little bit more on model monitoring here, because that's definitely its own sort of section of the exam. It kind of runs into some of these things that we've been talking about loss metrics and things of that nature. But so it's all a little bit of a blend. But conceptually, the idea with things that we want to look for as we talk about model monitoring here is that a model can perform well on your validation and test sets, but over time, after deployment, if the underlying data or the environment changes, the model can become less useful over time. So conceptually, we've been talking about training the model that's in production. We observe its performance in production. So kind of now we want to think about what happens after the fact, like a year or a couple years down the road. What's the kind of things that we need to be thinking about then? So an example here would be concept drift, which would be when the underlying assumptions of the model change. So for example, spammers can modify their emails to bypass existing spam filters. It's important to know this distinction around skew and drift. So skew would be when there's a difference in the input feature distribution in production compared to the training data, versus prediction drift would be when the input statistical distribution changes in production over time. So drift would be just over time, just the distributions of these things start to change. We have some various tools for monitoring that. Sorry, I think you all see the next slide at this point, but I'm not seeing it on my end, so give me a second here. Just one moment, y'all. I'm sorry for the technical hiccup on my side. All right, I think we're getting somewhere. Give me just one moment. Can you all see the slide? For me, it's kind of spinning in a circle, but I'm not sure, because I exited the session and then came back for a second. So I'm curious if you all can see it on your end. You can. I see some thumbs up coming in the chat. Okay. See the thumbs up coming in. I'm taking that. Well, more thumbs up coming in. So I'm taking that as a. I'm taking that as a yes here. So for model monitoring tools, um, so there are various tools that we have for tracking metrics during training. TensorFlow Profiler is used for analyzing and optimizing TensorFlow model performance. That can be used for profiling the performance of Vertex AI training jobs and visualizing results, and it integrates with Vertex TensorBoard. Or you have the so-called what-if tool, which is a visualization tool for exploring and understanding machine learning model behavior, predictions, and biases using interactive scenarios. So you basically do this in a notebook, and you'll display these different scenarios that can occur interactively inside that notebook. I want to touch very briefly here on explainable AI. Explainable AI is, to me, under the broader umbrella of model monitoring, because often we need to go explain our model predictions. The exam is liable to ask, okay, based on this type of model, data, all that good stuff, what is the appropriate what is the appropriate tool for explaining it? So with Vertex Explainable AI, that's a pretty key service that we have. Just gives us all kinds of different tools for explaining and interpreting the model's predictions and behaviors. It supports AutoML image and tabular models or custom trained TensorFlow image and tabular models. Its focus is generally around instance level feature attribution as opposed to more global level feature attribution. I'm just not having great luck with slides today. Just a little bit, just to talk through this while we. I think it's showing for all y'all, but just on my end, that's where we have problems with feature attribution. Vertex Explainable AI offers us some different ways of going about that. So sampled Shapley being one of them. Well, sampled Shapley establishes feature importance by assigning credit for the outcome to each feature. This is based around the idea of SHAP values, right? So SHAP values essentially tell us how much each feature contributed to the prediction of the outcome. So that's all supported inside of Vertex Explainable AI. You've got integrated gradients, which are mostly used for deep neural networks with image use cases. It integrates gradients along the path from a baseline input to the actual input. But then that's also extended in the form of explanation with ranked area integrals. So we can combine the integrated gradients method with additional steps to determine which regions of the image contributed the most to the outcome. So it's essentially just an extension of the integrated gradient approach. All right. There's only a couple exam questions on this kind of content. As soon as we get through those, we can break, and then we can move to the last section of this course. And the last section is a doozy, so and it's very important. So I want to make sure we're well braked and well rested for that. Just a quick one here. When there's a difference in the input feature distribution between the training data and the data in production, what is that called? Is that distribution drift, feature drift, training serving skew, or concept drift? This is a bit more of a definitional sort of question, so we can give about 30 seconds on this one. All right. Going to close this one in 5, 4, 3, 2, 1. All right, I see the most frequent selected answer was training serving skew, and that is the correct answer. It's basically a testing the definition of what training serving skew is. Like, okay, can we map the definition here? One more question before our break. That is, you are a data scientist at a startup and your team is working on a number of machine learning projects. Your team trained a TensorFlow deep neural network model for image recognition that works well and is about to be rolled out in production. You have been asked to demonstrate the inner workings of the model. What explainability technique would you use on Google Cloud? Think about a minute on this one. Okay, I'm going to close this one in about 5 seconds. Go 5, 4, 3, 2, 1. Oops. Oh, there we go. All right, the correct answer here is integrated gradient. The key here is that this is an image recognition problem, right? So integrated gradient is going to be our explainability tool here. If we have image data, Stapley is more for tabular data. Image data and image recognition problems, we want to use integrated gradient. PCA is not for explainability, that's for dimensionality reduction. And the what if tool analysis is actually for model monitoring. So model monitoring different scenarios versus explainability per se. All right. So this is actually perfect. We are right at about 50 after the hour. This is perfect. We have a 10-minute break. We will kick off again at the hour, and then we will get into, like I said, this last section of the course is really a doozy on security and pipelines. It's very important. So do what you got to do, and we'll be back at the top of the hour. Okay, we've hit the top of the hour here. I think we're ready to get started on the last quarter of the course here, and this is a fun one. So this is a pretty heavy piece. I'm gonna step through some of the last content here, and I'm aiming to take no more than 20 minutes, 25 minutes, absolute max, to go through this content. We're going to talk about security, IAM, all that good stuff. A little bit more tooling, pipelines and orchestration, which is another huge critical component of the exam. And then the back half of the hour is going to be all exam questions. And it's going to be some of the more difficult exam questions that there are. So this is a really good opportunity to really make sure you're listening, but also gauge just how ready that you're going to be for the exam too, or at least specifically on the exam questions on this type of content. So starting with IAM, because I want to cover some of this more security level stuff first. IAM is a framework and set of tools in Google Cloud for defining and managing permissions for users, groups, and services. This can be managed at the project level or the resource level. So the basic IAM roles that Vertex AI provides are predefined, like a Vertex AI administrator or user, a basic, like an owner, an editor, or a viewer, or custom. So you can create your own sets of permissions. Google does not like you to give more permissions than the bare basics. So the idea is don't give people more permissions than what they actually need. Talking a little bit about user managed versus managed notebooks. There's two major types of available Vertex AI notebooks. There's user managed, so those are customizable and ideal for users who require lots of control over their environment. So you choose a framework like TensorR or TensorFlow or PyTorch, what have you. You might need to do that if you have very specific requirements around networking or security. But there's also Google Cloud managed notebooks. So ones that integrate with BigQuery and cloud storage in the Jupyter Lab environment. You can schedule those for execution. There's automatic shutdown for idle instances, which saves on resources and compute. They can process data quickly by running a notebook on a Dataproc cluster or a serverless Spark cluster. They can be connected to a VPC network in the same project, or a shared network that you have access to, and then you can configure access to specific services via VPC. So an important set of tools here or an important service more broadly to talk about here is the Google Cloud Data Loss Prevention API. This is your catch-all for anything regarding particularly sensitive information. So this can de-identify sensitive data in text content. It can detect sensitive data and use de-identification transformations to mask, delete, or obscure the data. It's efficient in the sense that it can scale automatically with demand, and it includes risk analysis methods before de-identification to help assess and prioritize risks related to data storage and processing practices. So, and you'll have to know at some level the distinction between these techniques. We'll have an exam question later that's really good. I ripped it directly from Google Cloud's old sample exam. Tests the differences between these, but there's masking, so replacing characters with symbols such as asterisks. There could be tokenization, so like cryptographic hashing to replace instances with tokens. There's encryption, so replacing data with randomly generated or predetermined keys. And there's also bucketing, so replacing more identifiable values with less identifiable ones. It's important to know what federated learning is. as we talk about some of this privacy and security type stuff. So federated learning is a machine learning approach that would enable a model to be trained across multiple decentralized devices holding data samples without needing to go exchange them. That whole exchange process being where we get into just people getting access to data that they shouldn't. So the idea being, instead of aggregating data in a central server, federated learning can bring the model directly to the data source, so like mobile devices or hospital servers. This would inherently protect users' privacy because you can, again, you can tack on top of this using things like differential privacy and secure multi-party computation. Similarly, we can have latency benefits here by reducing the need for constant internet connectivity and data transmission. So the idea being here, the devices train the model on their local data, generate model updates, the central server collects the local updates, and then the updated global model is sent back to all devices. This more or less wraps up the content that I want to talk about around privacy, security, and things like that. Obviously, know about federated learning and what that is, and how that can be useful for various potential use cases. The data loss prevention API, obviously. Now we want to talk about orchestration frameworks. So the motivation here is, there is a lot of moving parts in a lot of these engineering problems and a lot of these machine learning problems broadly, because maybe you want to do something like train a model when new data is available, so you want it to respond to that event, or maybe there's just new data that's coming in all the time and you want something to run on a schedule. You want to send an alert when something happens based on the performance dipping below a certain value. I don't know, there's a ton of different permutations and possibilities when you need to orchestrate these things together. But the broader point being, there's a lot of multiple steps that are going on in these workflows, and you need some kind of framework, some kind of orchestrator to manage, automate, and optimize these processes. There's a lot of different options for that, which we're going to talk about. We run a pipeline sequentially, moving from one step to another based on pre-specified criteria. Let's start by talking about Kubeflow. So Kubeflow is an open source framework for deploying, managing, and scaling machine learning workflows on Kubernetes. Kubeflow leverages Kubernetes container orchestration capabilities to scale machine learning workflows based on demand. So we've got a consistent environment for machine learning development and deployment across different environments, whether that's on-prem, cloud, or some hybrid between the two. And basically, Kubeflow provides a framework for the creation of end-to-end machine learning pipelines. You can serve predictions via REST APIs or post requests, things of that nature. Now, Vertex AI pipelines, think of this as like Google, or specifically Vertex AI managed Kubeflow pipelines. That's how I personally conceive of this. It's basically a managed service on GCP as part of Vertex AI that enables users to create, deploy, and manage end-to-end machine learning workflows. So provides tools for orchestrating complex machine learning workflows like data ingestion, pre-processing, model training, evaluation, and deployment, supporting versioning of pipeline components. Vertex AI makes all of that very easy for us to do. That extends to visualization tools and monitoring dashboards. Users can create custom components using Python code. And again, this all integrates seamlessly. This goes for anything that you do in Vertex AI. These things are built to flow seamlessly and work well together. So then you've got Cloud Composer. So Cloud Composer is a little bit more complex. in the sense that the environment for it is always active. So it's not necessarily going to be the most cost-effective type of solution, but it is a fully managed workflow orchestration service on GCP based on Apache Airflow. So we can enable the automation of complex workflows and data pipelines, orchestrating tasks and dependencies across different services and systems. It does integrate seamlessly with other GCP services, much like Vertex AI Pipeline does. The workflows are represented as DAGs, that is directed acyclic graphs, where the nodes represent tasks and the edges represent dependencies between tasks. It provides Apache Airflow deployments for managing workflows. It is commonly used for data processing and ETL pipelines, as opposed to these more traditional machine learning use cases that we've been talking about with Vertex AI pipelines, workflow automation. Just an important thing I'd remember is that the environment for it is always running, it's always active. So how do you kick off Kubeflow pipelines? So there's a cloud scheduler that works via cron jobs. You can use pub/sub and cloud functions in a more event-based sort of way to respond to new events. Like, let's say, oh, there's a new file that's available in this cloud storage bucket. Now we need to go kick off this pipeline. You can use that. You can use Cloud Composer or Cloud Data Fusion if this is all part of a bigger data and process workflow, or you can use Cloud Build, which is kind of more of Google's GCP's CI/CD service offering. So a little bit about when to use each pipeline. I've been trying to talk about this as I go along this, but I want to more specifically talk about this and call it out, be more specific about this. We've already talked a little bit about TensorFlow Extended, TFX, but I did that in an earlier section, but TFX is recommended if you're already using TensorFlow and you're using lots of structured or textual data. It's useful for building end-to-end machine learning workflows within TensorFlow ecosystems. I already tried to touch on this when I talked about Cloud Composer, but I'm just gonna repeat myself like a broken record here. Cloud Composer is used to orchestrate data-driven workflows like ETL or batch processing. It's very good for that, but it's always active. So if you have cost concerns, just keep that in the back of your mind. Vertex AI Pipelines is designed for end-to-end machine learning development and deployment with support for monitoring and lineage. Again, you can really think of Vertex AI Pipelines as just Google managed Kubeflow, but we use this all in conjunction for deploying, orchestrating, and managing the workflow. It's all well suited for hybrid and multi-cloud environments and allows the users to define custom containerized components. Components can be dependencies, they can be functions, so on and so forth, but with execution on Kubernetes clusters. A little bit more on triggers and pipeline schedules. There are various ways to go kick this off. So I already talked about Cloud Scheduler for setting up cron jobs. Jupyter Notebooks with Vertex AI managed notebooks, you can do that. Cloud Functions, those are event-driven. Cloud Build, which is a CI/CD offering for, you can build Docker files, retrain models, push for custom training, so on and so forth. Cloud Run is one that I actually personally particularly like. That's for just specifically running these already Dockerized and containerized applications. So I built something before where you use GitHub Actions just to push a Docker image to the artifact registry, and then Cloud Run just kicks off that containerized application. Or you could do all of that in Cloud Build, which is, again, more of an in-house Google CI/CD approach. A few more things I want to talk about before we go to our exam questions. Lineage. So lineage is the tracking and recording of history and dependencies of artifacts and processes in machine learning workflows. Vertex AI Pipelines offers plenty of support and provision of this type of stuff. So data lineage tracks the origin and processing history of the data. Model lineage would track the training data, hyperparameters, and versions across the different models that we've run. Code lineage would track the execution path and dependencies of our code components, scripts, modules, functions, so on and so forth. And artifact lineage tracks all the factors that resulted in an artifact. So data, models, code, and configurations broadly. Last thing I want to talk about before our wham bam of exam questions at the end is Vertex ML metadata. That is a service specifically for management of metadata in machine learning workflows. So tracking and organizing and storing metadata related to machine learning artifacts like data sets, models, and training runs. Again, versioning, lineage, and dependencies, those would all be examples. We can go track and manage our machine learning experiments. So things like hyperparameters, metrics, and outcomes. Maintains a version history for our machine learning artifacts and facilitates model monitoring by capturing all that metadata. So the metadata can help us track things like drift detection, data quality, so on and so forth. This is always right about the point of the course where my voice really starts to hoarsen out and give up a little bit. Which is part of the reason why I have backloaded the course with a ton of exam questions. And it's going to be very centric around this content that I've just covered. So that is what we're going to spend the rest of the course doing here. I encourage as much participation in this as possible because, again, that makes it's just a whole lot more fun for me. And again, I hope you've been keeping track as we go along here about how many you've been getting right and how many you've been getting wrong, because that's really going to be an excellent gauge for you about how prepared you are for the exam. I've intentionally structured things to represent the varying degrees of difficulty of questions on the exam as best I possibly can. So without further ado, let's get into our questions. So a national hospital is leveraging GCP and a cell phone app to build a machine learning model to forecast heart attacks based on age, gender, exercise, heart rate, blood pressure, and more. Since the health data is highly sensitive personal information and cannot be stored in cloud databases, how should you train and deploy the ML model? Let's take 45 seconds or so on this one. I'll close this one out in about 10 seconds or so. Let's go 5, 4, 3, 2, 1. Oh, wow. Definitely have a little bit of a spread here. The correct answer here is federated learning. So this is a traditional use case of federated learning where you've got data which is stored in different hospitals and they can't store them in cloud databases because of privacy and security concerns. So federated learning will collect the data and train them with algorithms across multiple decentralized devices rather than storing them in rather than exchanging them and doing all that kind of stuff, which can get us in trouble. DLP API is more around when we have sensitive data and we need to figure out what do we do with it? How do we clear that up? How do we clean it up? That's actually a great segue to the next question, which is this one here around you developed a tree-based model based on an extensive feature set of user behavioral data. The tree model has been in production for 6 months. New regulations were just introduced that require anonymizing PII, which you have in your feature sets, using the DLP API. You want to update your model pipeline to adhere to the new regulations while minimizing a reduction in model performance. What should you do? Take 2 minutes on this one. This one's hard. Take your time and think about it. There's no reason to rush this. Oops. Sorry. Don't know if the slides were doing silly things for y'all. Yeah, sorry about that. I hit the next button because there's sometimes a lag on what you all see versus what I see. So again, let's take a fresh 2 minutes on this question. It's hard. Let's try to wrap this one up. Make your best guess about this one. Let's go 15 seconds or so. I see the rate coming in on this one's a little bit lower. I don't know if that's because of the goof up on my end with getting on the right slide, but just make sure you get this, or because the question's hard, because it is. But let's just get your best get your best guess in for this one. I'm going to close this one off in 5, 4, 3, 2, 1. Okay. The correct option here is C. Use key-based hashes to tokenize the features containing PII data and train the model from scratch. So here's a few of the concepts here. So one piece here is that masking doesn't enforce referential integrity. Key-based hashing does. Nobody selected deterministic encryption, but that is a reversible procedure, so that's not necessarily going to guarantee that we're going to meet the necessary privacy and regulatory standards here. If we do redacting the features, it's going to cause their performance to suffer, so that's not ideal. But then here's another piece here. It's not sufficient to tune the model from the last checkpoint. You have to train the model from scratch. And the reason for that is if there's new regulations here, if the model has already seen data from the past, like if it's already learned sensitive data, then it's already learned sensitive data. We have to retrain it. So if it's memorized sensitive information, doesn't matter what else we do. That's not kosher. We have to train the model from scratch. This question that was lifted directly from Google sample exam questions, which again I brought these up before. Those are some of the absolute most difficult that you could possibly have to deal with. So there's a reason I've picked this one and tried to call it out specifically. I can't see it yet on my end here, but I think you all can see the next question now, right? Can you all see the question, which is you created a machine learning model and want to use the data to refresh your model as soon as new data is available in a Google Cloud Storage bucket? Can you see that one? Awesome. Okay. So I can't see it on my end, but you can. But I have it open on a different screen offline. So we'll start there and wait for it to show up on my end. As part of your CI/CD workflow, you want to automatically run a Kubeflow pipelines training job on GKE, Google Kubernetes Engine. How should you design this workflow with the least effort and in the most managed way? Let's take a couple minutes on this one. This is another hard, like these pipeline ones in general, in my opinion, are some of the most challenging questions that Google offers. So take a couple minutes on this. Take another 30 seconds or so here. All right. Let's close this one out in 5, 4, 3, 2, 1. All right. Whoa, that's impressive. I'm the yeah, 100% of you who gave your shot at this one got the correct answer. The correct answer is configure a cloud storage trigger to send a message to a pub subtopic when a new file is available in a storage bucket. Use a pub sub triggered cloud function to start the training job on GKE. That's a very managed solution, and it's very low effort. That's kind of the things that we're looking for here. When we start talking about like checking the timestamp of objects in cloud storage to see if there's no new files since the last run, you're getting into higher effort type of stuff. Creating new lightweight Python clients is not a very managed solution. Starting the job on Google Kubernetes engine, it's just, we want the lowest effort and most managed type of solution possible. Next question here is, which y'all might have seen as I was trying to correct the slides. We've got, you are an ML ops engineer and you deployed a Kubeflow pipeline on Vertex AI pipelines. Which Google Cloud feature will help you track lineage with your Vertex AI pipelines? Take a minute. This one is a little bit more straightforward than some of these last ones. So let's try to keep this one to about 45 seconds or so. All right, let's take another 10 seconds. Get your best guess in here. So 5, 4, 3, 2, 1. And the correct answer here is Vertex AI ML metadata. Artifact registry is actually for storing Docker images. So probably not our go-to here with lineage more broadly. Model monitoring can help us track the drift and skew and all that good stuff. Vertex AI ML metadata is our correct one here. Lineage being a classic case of metadata. What is not a recommended way to invoke a Kubeflow pipeline? Is that Cloud Scheduler? Is it responding to an event using PubSub and Cloud Functions? Is it Cloud Composer and Cloud Build? Or is it directly using BigQuery, which is not a recommended way? This is a little bit simpler of a question. Let's go with 30 seconds or so for this one. You want to pace yourself a little bit on the exam because you have an average of about 2 minutes per question. Some of them you might be staring at for like 4 or 5 minutes. trying to unpack what are the key things the question's saying, and some of them you can answer quickly. So if you can answer one quickly, you generally want to, just to allow yourself as much time as possible. All right, take another 5 seconds on this one. Let's go 5, 4, 3, 2, 1. And the answer is directly using BigQuery. The reason for that is because that is not a way to invoke a Kubeflow pipeline. It doesn't. You can't do it. You can't use BigQuery to invoke a Kubeflow pipeline. You can use Cloud Build. You can use Cloud Composer. So one pipeline to kick off another pipeline. If that's what you need to do, you could do it. Cloud Scheduler and Pub Sub and Cloud Functions are kind of typical classic use cases. But yeah, you can't use BigQuery to kick off a pipeline. We're on kind of our home stretch here, but next question. You use Vertex AI Workbench notebooks to build a model in TensorFlow. The notebook loads data from cloud storage, uses TensorFlow transform to pre-process data, uses built-in TensorFlow operations to define a sequential Keras model, trains and evaluates the model, and saves the trained model to cloud storage for serving. You want to orchestrate the model retraining pipeline to run on a weekly schedule while minimizing running costs, refactoring steps, and monitoring steps. What should you do? This one's wordy, so let's take a couple minutes on it. Take another 30 seconds or so for this one. Okay, close this one in 5, 4, 3, 2, 1. Okay. Our correct answer here is use TensorFlow Extended, TFX, with Google Cloud Executors to define your pipeline, and use Cloud Scheduler to automate the pipeline to run on Vertex AI pipelines. There's a few different things going on with this question. That tends to be the case with some of these more pipeline-heavy questions. First and foremost, we already are using TensorFlow. Like we built a model in TensorFlow. We're using TensorFlow transfer. There's all this TensorFlow stuff going on. So for that reason, we want to leverage TensorFlow extended. If we start using Kubeflow pipelines, that's getting into refactoring type of stuff, which we ideally don't want to do. Similarly, that second option with Cloud Composer, we want to minimize running costs. Cloud Composer is generally not going to minimize running costs for us because, like I said, the environment with it is always active. The first one, nobody selected that, but Vertex AI Workbench doesn't provide alerts. Also, Cloud Composer doesn't provide machine learning specific monitoring either. So that's there's multiple reasons like Cloud Composer doesn't really make sense for this use case. So those of you who selected the last option, where we're going with TensorFlow extended, Google Cloud Executors, Cloud Scheduler, Vertex AI pipelines, good job. This is another pretty hard question. Which, speaking of that, we're going to move on to another hard question, which is, you are a machine learning engineer of a fintech company building a real-time prediction engine that streams files that may contain PII to GCP. You want to use the Cloud Data Loss Prevention API to scan the files. How should you ensure that the PII is not accessible by unauthorized individuals? This is another one I ripped from Google Cloud's own sample questions, and it's hard. So, take a couple minutes, think about it. We'll regroup. Take another 15 seconds or so for this one. All right, I'm going to close this one in 5, 4, 3, 2, 1. I really wish we had the Jeopardy music for these. It would make this more fun. But let's see what y'all thought. Make sure all your answers in. Yeah, nay. Let's see what you thought. Good job. The most selected answer is streaming all files to Google Cloud and then write the data to BigQuery, periodically conduct a bulk scan of the table using the data loss prevention API. That is correct. That is the best possible practice that we can do here with this whole streaming files type of situation. One idea here is BigQuery is a good tool for this kind of bulk processing and integrating with the data loss prevention API. Y'all successfully picked BigQuery options here. In general here, what we want to do is wait for the data to come in and then do this bulk processing. It seems inefficient, at least the way I read the question, to write the data in batches while the data is being written. So once the data is fully written, we can run the data loss prevention API. This is a tough one. Now we'll move on to our last question, and I did not save the easiest for last. You want to send bi-weekly scheduled emails to customers that are expected to spend above a variable threshold. After setting up a new Google Cloud project, you use Vertex AI Workbench to develop model training and batch inference with an XGBoost model on the transactional data stored in cloud storage. You want to automate the end-to-end pipeline that will securely provide the predictions while minimizing cost and code maintenance. What should you do? You have ABCD, 4 options here, and this is wordy. We'll take another couple minutes or so for this. Let's take another 15 seconds or so for this one. All right, let's go. 5, 4, 3, 2, 1. Okay. Majority of you selected A, and that is the correct answer. Create a scheduled pipeline on Vertex AI pipelines that accesses the data from cloud storage, uses Vertex AI to perform training and batch prediction, and outputs a file in a cloud storage bucket that contains a list of all customer emails and expected spending. So there's a few things wrong with each of the other options here. The main thing wrong with option B, nobody selected that, but Cloud Composer, we already have established Cloud Composer is not going to minimize cost because of the always running environment. So good, y'all are getting that down. That's good. Creating a scheduled notebook on Vertex AI Workbench that does all this stuff, that's not going to minimize code maintenance. We want to minimize code maintenance, code interaction, all that kind of stuff. And yeah, we're this last option, again, it's using Cloud Composer. And you don't want to send potentially sensitive information via email. That's not a good practice either. So that's an additional thing that's wrong with that's wrong with option D. So that actually is the end of our course here. We're wrapping up here with actually a few additional minutes to spare ahead of the top of the hour. So just a few last comments that I'm going to make. And by the way, I'll stick around for a few minutes after this in the Q&A and attendee chat to see if there's anything you'd like to know about the exam or questions or anything of that nature. Nobody actually knows because Google doesn't publish this. AWS does, but Google doesn't. How well do you actually need to score on this exam to pass? There are rumors, but nothing really official, at least as far as anything that I personally found credible. Generally, I would say if you scored 60 to 70% on the practice questions we've run through today, you're probably in very good shape. If you're taking Google's sample questions, you could be at 50% for those because those are harder than the average question on the actual exam. If not, and you didn't score that well, then don't freak out. Don't worry about it. Continue reviewing, reading, and practicing on the topics that you've struggled with. I hope the way that I've structured and organized this course, that it's really helped you to be able to laser focus on, maybe you did well on particular sections, but not so well on other sections, or there are just key concepts that you kept running into, and maybe you figure out what you need to read more about. I hope that you had the opportunity to really be able to think about those things as we went through this course. Just a couple, just closing this out with some shameless plugs here. If you'd like to connect with me, I am Richard on Data on YouTube. I have a lot of content over there. It's been a while since I've uploaded in there, but there's definitely a lot of content there you can go check out, or you can connect with me on LinkedIn. My name is Richard Bryant, and my name on there is R.I. Bryan. And best of luck to you all on the exam. I hope this has been useful, and appreciate you all spending 4 hours listening to me drone on here. And with that, I am actually going to turn it back over to Brittany.
All right. Thank you, everyone, for attending our course. We hope you benefited from the live course and hope to see you on other O'Reilly live courses in the future. Thanks again. Enjoy the rest of your day. Goodbye, everyone.